Knowing whether a reaction occurs tells us whether the OA is above or below the RA. And you can actually, if you have data on reactions, you can build a reduction table like this. And this is a question that's always given on tests and always given on exams. I will build a reduction table just like page 7 in your booklet, knowing the following reactions. Okay, the columns are going to react with each of the rows. So these were reactants, and these column headings were reactants, and they were mixed together. And we see in the boxes what happened. Okay. So when bromide was paired with bromine, there was no reaction. When chlorine was combined with bromide, there was no reaction. But when iodide was paired with bromine, there was this new pink-purple color. There was a reaction. So I'm going to get that heading out, reduction table. Okay. So this is half reactions, and they have to be GERs. Okay, we got to build this from this information. Now, you don't need all of the information. I'm going to process as much as I can until I've built a table, and then I can just use the rest as a double check. So I'm going to start with this middle column to process first. There was a new yellow-brown color when chlorine reacted with bromide. Okay? So I know the oxidizing agent must be above the reducing agent. Okay, I just got to figure out which one is which, and then I know the order of whether bromine is above or below chloride or chlorine. So the way we give these to you, the columns and the rows will always be the same type of agent. And this is where just going to your data table will often help you. If you flip to page 7, it tells you whether they're OAs or RAs, or you can use the charges if they're not in the table. These are all neutral. Okay. And bromide is minus. So if we went from bromine to bromide, to go from 0 to minus, you would have to gain an electron. Okay, that's the only way you're going to make it minus. So gaining electrons reduced. Okay, so this guy is reduced, so this must be an oxidizing agent. And all of that top columns are all OAs. Okay? All of these guys are reducing agents. They're where the electrons, they're the result of the electrons being gained. Now, sometimes the top is OAs and sometimes the top is RAs, but they'll always be the same type. So bromine, Br2, Cl2, I2. Okay? All of those will always be the same type of agent. Okay? So they're all OAs. So we have, going back to the yellow-brown color, we know there's a reaction. We know the OA is above the RA. So we know the oxidizing agent is Cl2. In the first column must be above Br minus in the second column. Okay. The first column is always our OAs, the second column is our RAs, and we now know which is above or below the other. If I pick, you can kind of pick whatever one of these you want. Okay. If you're wondering how did I decide which ones to pick, it really doesn't matter. You just pick a few until you start building an order. I'm going to pick this other reaction. We see a reaction, so the OA is above the RA, and the OA is going to be Br2, and the RA was I minus in this case, and we do see a new color, so the I minus must be below. Okay, and those two tests alone are kind of enough to give us a bit of an order. we have the half reaction with any Cl species in it is above Br, and we know the I- species have to be below the Br ones. So I'm going to build a table just from analyzing those 2 points. Okay? And I know this is the first table I built, and I'll do a second one which will help make it a bit more even clearer. So I've got to build a half reactions. We have to have OAs on the left. So I'm going to start building this coal-chlorine half reaction, and I have to build it above a bromine-bromide half reaction. So my OA is Cl2. Okay. Our table tells us that the Cl ends up as chloride. We start with Cl2, so we're going to need 2 chlorides. Okay. And in reduction tables, we're always writing the gaining of electrons on the reactant side. Okay. And we're going from 0 to +1, sorry, 0 to -1. When we go from chlorine, that's 0, and each of those Cl's are 0, and we're making 2 minuses because there's 2 Cl's on both sides. There's 1 electron in each process, so I have to double put 2 electrons, 1 for each of the Cl's. So that reaction is on the top because this was on the top. We know Br is below it, so the Br minus must be below. Okay. That's what the fact there was a reaction tells us. And then I got to build the whole half reaction knowing that all the pieces of Br sit below it. Okay. Our table up above shows us that Br as an OA is a diatomic form. If there's 2 Brs, we must get 2 Br minuses, and we kind of see the same layout that we need 1 electron with each of the Brs, and there's 2 on both sides. Okay. So what we've built has our chlorine above our bromide. If we keep going with our second point, we don't have to rebuild a bromine half reaction. We already have bromine right here, and we know iodide has to be below it. That's the only way for it to be spontaneous, and then I can fill in that whole half reaction. These are all halogens, so we see the same type of layout. And that layout of the table matches the yellow brown data point, and it matches the purple pink data point with bromine reacting with iodide. We could do a quick little check. If I look at just this column, okay, this column I2, iodine, okay, iodide is the minus ion, iodine is the diatomic, that reacted with nothing. Okay? So that's saying that as an OA should have all the RAs above it. And that's what we see. We see Cl is above it, Br is above it, and I minus is actually even with it. Now I haven't talked about what if 2 things are even. What if the OA is exactly next to the RA? That still comes out non-spontaneous. If you think of the OA being above the RA, that's like kind of going downhill. If the OA is below the RA, that's kind of like going uphill, which doesn't happen, and the OA and the RA next to each other is like a flat piece of ground. But nothing rolls on a flat piece of ground. It's not going to spontaneously start rolling. So the table we built does match this last column. Okay. So this is your first example of building a redox table. Most students are still a little confused with this first one, so I'm going to go into a second one. So this is our last big example of this lesson. I got one more small slide, but we're going to create another reduction table, just like the format of our data booklet on page 7. And we're going to use, instead of getting our data in a table, we just got 3 equations now. You might actually find this a little easier. So again, I'm going to, so looking at the first one, I'll get my layout, reduction table. That's what I need to build. And I see cobalt in this reaction, indium, copper, and palladium. End up with 4 half reactions. So in our first one, I've got cobalt and indium. I don't care about the count. That just balances the electrons. I just care about what's the OA and what's the RA. So here's cobalt 2 plus, and it's going to neutral cobalt. Okay. What I'm trying to do is figure out what's the OA is the point of what I'm doing, because I know the OA is on top because it's spontaneous. So 2 plus to 0, that's 2 electrons, which I don't really care about, and is that a gain or a loss? So if it gained electrons, it would go neutral, so that works. 2 plus 2 electrons would make it neutral. So that's gaining electrons. Which agent is that? Cobalt 2 plus gained electrons, so that's the gaining electrons reduced, that's the GER. So this was reduced, so as an agent, this was the OA. Okay. Once you find one agent, you know the other reactant should be the RA. Now we'll go and talk about it, but we really don't need to. If you find one agent, you know the other's the opposite. The indium goes from neutral to 3 plus, so that had to lose electrons to become 3 plus. So the indium, which I'm using green with, was oxidized, so the type of agent it is the opposite, so it was a reducing agent. Now, one thing you'll find as a trend, neutral metals are always RAs. And this is a really helpful trend. I'm going to flip back in my data booklet, and this is why it's so much easier for me, because I know so many trends. If you look for the neutral metals, no charges, there's a whole bunch of neutral metals. There's cobalt, that was nickel. We saw gold and silver up above. There's copper. They're all on the right-hand column. They're all RA. So there's no exceptions to that. So as soon as you see a neutral metal, you know it's a reducing agent. Aha, there's another neutral metal. I know that's an RA. PD solid, that's a neutral metal. That has to be an RA. There's no exception. So this trend can really speed things up. Okay? The way this reaction was laid out, all the OAs were written first and all the RAs were written second. So now I can start building a table. I know my OA, I know my RA. It was spontaneous, so the oxidizing agent has to be above the reducing agent. I'm going to start writing that as an equation. Now I'm going to leave some space in between my equations because I don't know if something's going to be above or below it as I work through the second or third reaction. So OA is cobalt 2 plus. And let's get out that whole half reaction before we move on. Cobalt 2 plus, we can see in our reaction, makes just cobalt. And we're going 2 plus to 0. So that's going to require 2 electrons to go from 2 plus to 0. And the key here is I started with this as our OA. I know indium as an RA has to be below it. Okay. Now I left some space in between the two products so I can stick something in between if I need to. So indium is our product, and this nicely gives us cobalt 2+ as our OA is above indium neutral as our RA. Okay? And then I have to look at the half reaction and get all the pieces out. We have indium as neutral indium here. Okay? What form of indium do we have to put on the other side? That's the 3+ form that we have in this question. And we got 3+ going neutral, so there's 3 electrons in that half reaction. Okay. Some of the reactions look backwards compared to what we see up above because we're only writing reductions. Any of the reactions, all the oxidations in our reactions, they're going to be backwards from what we see. Okay. What actually happens in this reaction is this half reaction going backwards. So I've decoded that first reaction in order, built 2 half reactions. So let's dive into the second. It's spontaneous, so the OA is above the RA again. And if a chemical repeats, we're not going to write it again. So I have copper is going to be above cobalt. So copper is above cobalt, okay, because it's spontaneous. Do I have any of those chemicals already? Yes, I've got there's cobalt as the RA from the second half reaction. I already put an equation with cobalt in it. So I don't have to write that again, but I know the copper half reaction, this OA must be above it. Copper 2+ has to be above the cobalt half reaction to make it spontaneous. So I just have to build that copper half reaction above the cobalt. So I've got copper 2+ going to neutral copper. Okay. I've been leaving the states out throughout this slide just to try to make it cleaner and easier to read. 2+ to neutral would be 2 electrons again. I'm just taking out my zeros again, trying to make this as clean as possible. Okay. Our last piece of evidence is we've got copper. Okay, we got that in our table. That's reacting with PD, but there's no evidence. This was non-spontaneous. This didn't happen. So now the OA has to be below the RA. The OA is copper 2+, and PD must be above it. So there's copper that we have already as an OA, and there's our copper. So we don't have to repeat that OA again, but palladium has to be above it. Okay. Now, unfortunately, this is going to be easier for me than you. I got to make a little bit of room. Now, on the smartboard, it was easier for me to pull things down. Hopefully, you have a little bit of space above the copper to stick in a half reaction with PD. Okay. Now I've got to somehow build a half reaction. From this, we typically look at the products to figure out the other chemical, and there was no evidence. We don't see any products. Any thoughts of where I could figure out the most common charge for PD? Yeah, your periodic table. So we've got to find a PD which is palladium. It's atomic number 46, and the most common charge is 2+ on the table. Okay, so that's what I'm going to use. PD2+ plus 2 electrons makes elemental palladium. Okay? And this would be the corresponding redox table based on that experimental data. Okay? Our table matches all three reactions. First reaction, cobalt above indium, cobalt above indium. We have to have copper above cobalt from the second reaction. We've got our copper above cobalt, and our last reaction, our OA, is below the RA, our only non-spontaneous reaction. Okay. So that's your second and last building redox table for this lesson. Disproportionation is a weird circumstance where you have the same type of species as both agents, as the OA and the RA. Now you're going to need an example to make some sense of this. Same type of species as the oxidizing agent and reducing agent. One example that you can have the same type of species acting as both agents, and it's actually spontaneous, is copper +1 can react with itself. Now you need a different copper 1+. The same chemical can't gain and lose at the same time. Okay? But if you have multiple copper plus ions, one of them can act as the OA and the other can act as the RA. So I'll start with the oxidizing agent version first. I'm going to have to run through all that vocabulary. So if that's the oxidizing agent, what it's actually going to do to itself, okay, it's going to oxidize the other chemical, but itself, that copper plus at the beginning of that red line is going to get reduced. It's going to be a GR. Okay? It's the oxidizing agent, so it's always what happens to it is the opposite of oxidation is reduction. So it's going to gain electrons. Okay? So that copper is going to gain electrons, and you often have to look at your data table to see what possible charges are there. So as copper gains an electron, well, if it gained 1, it would be neutral, and we definitely know that copper can become neutral. Okay? There's no negative coppers. Okay? If you look at page 7 on your booklet, none of the metals become negative, so that's how I know it's a gain of 1 electron, +1 to neutral. So that's what the OA copper plus does. If I look at the reducing agent one, okay, the reducing agent is going to cause reduction in the other chemical. Itself is going to be the LEO. It's going to get oxidized. It's going to lose an electron or 2. And we have to look in our table to see what possible charges are there greater than +1. If it loses 1 electron, it's +1, 1 electron, it'll become +2. If it loses 2 electrons, it'll become +3. But we only see the 2+ type in our booklet. Okay? Copper +1, its only option is to lose 1 electron and become +2. Okay? And this is an example of disproportionation. We have the same chemical, copper +1, one acting as the OA, one reacting as the RA, making 2 different forms of copper, the elemental copper and the 2+ version of copper. Okay? And this is spontaneous. There's lots of other possible disproportionations. We'll look at some other ones later. I'm not going to write these out. Water can potentially react with water. Okay? You see water in your redox table as an OA and an RA. so it could potentially disproportionate. Or a lot of the other metals with charges, iron 2 plus, can potentially react with iron 2 plus. Okay? The key being disproportionation has the same type of species acting as both the oxidizing agent and the reducing agent. And maybe make a little star on this page. You always get at least one question on your test